Hi guys, just going to give you a quick talk on work and energy, which is uh, 10.1. So it's the first part of chapter 10. So we're going to talk about what is energy and how do we measure it. Does energy ever disappear? And what is the scientific meaning of work? So I just wanted to start off with a quote from Richard Feynman, which for me puts energy into perspective. So, there is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know, and the law is called conservation of energy. And it states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is the most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete, it is just a strange fact. We can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. So there's some number that a system has, and once it's finished doing something, it has the same number again, albeit in a different form. And we call this the conservation of energy. So you'll be familiar with some of these, I'm sure. So we've got different stores of energy. So there are different places that we can store energy, and we've got the gravitational potential store. So if you raise an object in a gravitational field, an object is now in a gravitational field, it's got some gravitational potential energy. If it's travelling, it's got kinetic energy. If it's vibrating, it's got some thermal energy. Or if it's stretched, it's got some elastic energy. There are also ways of transferring energy. So moving energy from one place to another. You can do that by radiation, e.g. light. So energy gets from the sun to Earth by the electromagnetic spectrum. You can transfer it electrically. So chemical energy from a battery might get into a small light or into your phones through electrical circuits, or you can transfer energy mechanically, i.e. sound. So sound from a speaker can transfer through the air, get to your ears. Now, what is the unit of energy? The unit of energy is the joule. So capital J, don't use lowercase j because it'll be marked wrong in an exam, because joule is the name of somebody. And 1 joule is the energy needed to raise 1 newton through a height of 1 metre. And so the principle of conservation of energy, which I alluded to earlier, is energy cannot be created or destroyed. In fact, it is just transferred from one store to another. So it's just transferred. So, the next thing I want to talk about is an equation that pops up all over physics. And that equation is work done equals force times distance. And we will have used this already, but this is an equation that pops up everywhere. And you might see it as W equals FD, F times D, like this. Now work done is measured in joules, and it is energy. It's the energy done by a system. So for example, if a 2 Newton weight is raised by 5 metres, then 10 joules of work is done on the weight. Something to consider here, force is a vector. So because force is a vector, excuse me, we can split the force component acting on an object. I just want to give you a little example of that. So if usually everything is in a straight line, so if the force on a car was here, and it travelled this distance, then we're happy that the work done is going to be F times S. However, if the force is at an angle to the distance, then say for example, I don't know, we had a boat is a classic example. Say this is my boat and it's moving this way, but the force is like coming across the sails this way. Then how do you work out what the work done is? Well, if we redraw this over here, we've got sort of the distance it will go this way, and F here. So, but we have to have them going in the same direction. So we're only interested in the force that acts in the same direction here. So what we do is we split our F into parallel and perpendicular to S with this theta here. So this would be F sine theta, and this would be F cos theta. So what we would actually have is W equals S times F cos theta. And actually, if we look back here to this example here, and you look at the shape of the cos graph, it is maximum at theta equals 0, which would be the case here because they are actually parallel, so theta would be 0. Don't know if you can hear that. That's my babe waking up, so I'm just going to go and sort her out. Hey, sorry about that. Yep, so the force is a vector, so when the cos of theta is 0, we get maximum, so that just becomes 1. So the equation sort of goes down to this one here. But when it's at an angle, we have to use F cos theta. So again, we've got our equation. Work done is force times distance. So if we have a force times distance graph, so force and distance with, I don't know, something like that, means that we can work out if the area under the graph is going to be the work done. So for this one here, that's when the force is constant. So here, the energy or the work done, or we can call it energy, is just going to be F times S. But for some scenarios, we have a graph that looks a bit like this. So, I don't know. You would have studied springs. Now, the energy stored in a spring is a half times, how was it? F times delta L. That's how it was. But that is just work done is force times distance, right? Because there's your force, there's your distance, there's your work done. But, excuse me, it's obvious to see that there's more force in a spring when you pull the spring out further. That's quite obvious. There's more force in the spring when you pull the spring out further. So we'd expect a triangle shape. Now, what's the area of a triangle? Well, it's half base times height. So therefore, it's very obvious to see that the work done, or the work held in a spring, is going to be a half base times height, or energy stored in a spring is a half F delta L. So that was just a very quick talk on work and energy. Now, so hopefully we've talked about, well, hopefully you'll be able to know is what is energy and how do you measure it? Does energy ever disappear? And what is the scientific meaning of work? Feel free to comment if there's anything you're not too sure on.